Welcome back to the regression series using the Possum dataset. I assume you have already loaded the dataset into your R environment. In this video, I will show you how to incorporate a categorical variable into a linear regression model. The new concept we discuss here is the treatment of a categorical data. So I will focus on how to understand those results properly. Let's start by checking which variables in our dataset are categorical. This structure function shows us the structure of each column in the data. The variable sex appears as a candidate. It represents the biological sex of the possums and should be treated as a categorical factor. The table function shows the number of males and females, represented by M for males and F for females. The structure function applied to sex column using $sign confirms whether sex is already a factor or not. Using the functions like factor and relevel, we explicitly set M for male as the reference group so we can interpret female effects relative to males. Let's now run our regression model, where the only new part is the inclusion of the categorical variable sex. Here is the output of model summary. Let's focus on the relevant part of the model output. The intercept have a value of 40.79 that describes the predicted head length for male possums when total length is equal to 0. Total length value equal to 0.60 tells us that for every 1 centimeter increase in body length, head length increases by 0.60 centimeter for males. The coefficient sexf has a value of minus 1.61, which explains that controlling for body length, on average, female possums have heads that are 1.61 centimeter shorter than males. This difference is statistically significant at p-value equal to 0.017, which indicates that sex is an important predictor. Next, we use box plot function to visually compare head lengths between males and females. The output of box plot command shows the head length distribution for male and female possums. The separation between the boxes reflects the estimated difference we saw in the regression. This visualization confirms that females tend to have shorter heads than males in this dataset. Next, we validate our regression model by checking whether it satisfies the key assumptions. We run the following commands in R. This generates 4 diagnostic plots: residuals versus fitted plot, normal QQ plot, scale location plot, and residual versus leverage plot, or we can call it Cook's distance plot. Residuals versus fitted plots. This plot helps assess two key assumptions of linear regression: linearity and homoscedasticity. We expect to see a random scatter or a cloud of residuals around the horizontal line at 0. No clear pattern suggests that the relationship between predictors and the response is approximately linear. Consistent spread of residuals across fitted values suggests homoscedasticity, that is, constant variance. In our model, the absence of visible structure or funnel shapes in the residuals versus fitted plot supports the assumption that both linearity and homoscedasticity are reasonably satisfied. The normal QQ plot checks whether residuals are normally distributed or not. Points should fall roughly along the diagonal red line. Minor deviations are fine, but major S-shaped curves would indicate violations. In our case, there is no issue with the normality. Next, we look at scale location plot to test for homoscedasticity. A flat horizontal band of points is what we want. If the plot fans out like a funnel, it suggests heteroscedasticity. In our case, we see a flat horizontal band of points, which confirms homoscedasticity. And finally, we analyze residuals versus leverage plot. This plot highlights influential observations that could distort the model. Spikes above the red cutoff line indicate influential points that need closer examination. We observe no abnormality here, And finally, these diagnostic plots confirm that our model's p-values, confidence intervals, and inferences are statistically reliable. And that's all for this video. Thank you for watching.